Hello everyone, it's Cheyenne, and today we're going to be discussing and practicing related rates problems. So to start this lesson off, in calculus, related rates problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are already known. Rates of change are usually written with respect to time, so all of these practice problems that you're going to see later are written with respect to time. I'm pretty sure, at least as far as I can recall, we haven't done anything other than that in our calculus class, so that's what you're going to be learning today. So before learning this, we were talking about implicit differentiation and stuff like that, and we didn't really see anywhere that that could be applied, but related rates questions do have a very important real-world application. Science and engineering often relate quantities to each other. Related rates are used commonly in these fields. So if you're considering maybe majoring in engineering or science, some of the science fields, you definitely need to know these. These are very important and not something that you should forget. Finally, our objective is to successfully complete and comprehend multiple related rates problems. So if you want to learn all about related rates and to see some practice problems done, just keep watching. Okay, so our first question says, a spherical balloon is inflated with helium at the rate of 100 pi feet cubed per minute. The first part of the question asks, how fast is the balloon radius increasing when the radius is 5 feet? First thing I like to do with these questions is I like to write what I know and what I don't know, just so I can see what I need to get to, what I already have, etc. In this particular equation, we know that the radius is 5 feet because it's asking how fast is the radius increasing when the radius is 5 feet. So we can write r equals 5 feet. So now the only other thing that we know is that the balloon is being inflated with helium at a rate of 100 pi feet cubed per minute. So whenever we are given a rate, we cannot write just, for example, r equals 5 feet because it is changing. Our rate is changing. So whenever we have a rate, we have to write something like d. For this one, I would do dv over dt because your volume is changing. So dv over dt rather than just v, because when v is changing, you can't just write v equals 100 pi. So dv over dt equals 100 pi feet cubed per minute. Now it is asking how fast the balloon's radius is increasing, so it's asking for another rate. So we would write dr over dt, because we're doing this all in respect to time. We're going to put a question mark next to that. That's what I usually like to do because that's what we're looking for. We don't know that quantity yet. So now, because we're talking about volume, we want to use the volume equation for a spherical shape, which you should have memorized because they don't always give this to you on problems. This one, for example, does not give you that equation, so you would need to know that. So our equation for volume is V equals 4/3 pi r cubed and I apologize for the shadow. I'm a lefty and I have a light beside me to give the video better lighting, so it kind of covers up when I'm writing, but I cannot help which hand I write with. Moving on, now we would differentiate this equation. I actually just screwed up on doing that, so that's why that's all crossed out. But what we need to do is differentiate this original equation. The first thing we would do is write dv over dt, because we're doing this in respect to time, equals, and then we would keep the 4/3 because 4/3 is constant. Then we still have the pi r cubed. The pi is constant as well. Then we have to bring the 3 in front of the r, so again we have another number, and then it would be r squared, not cubed, squared. And then we would have to write dr dt afterward, and that would be our new equation. So now we already know what dv dt is because it was given. It's 100 pi feet cubed per minute, so we can plug that in. Equals 4/3 stays the same, pi stays the same, the 3 stays the same, and we do know r, which is 5 feet, so r squared, 5 squared is 25, and dr dt we still do not know, so we're just going to leave that as is. So now we're going to plug all of this into our calculator. 4/3 pi times 3 times 25. We should get 100 pi when we multiply all of these out. So to isolate dr dt, we have to divide this whole quantity out of here and divide the 100 pi feet cubed per minute by it. So like I said, this is 100 pi. That cancels out. Divide by 100 pi, and we are left with 1 foot cubed per minute. And that is equal to dr dt. So the balloon's radius is increasing when the radius is 5 feet at 1 feet cubed per minute. So now we're moving on to the second part of this question, and it asks how fast is the surface area increasing when the radius is 5 feet. So again, we know that our radius is 5 feet. We're just writing down everything we know. We also know from the last problem that dv dt is 100 pi feet cubed per minute. Feet cubed per minute, and I'm just writing down everything we know. We might not end up using it. It depends on the equation that we need to use for surface area. We now know dr dt because we just solved for that. Dr dt is simply 1 foot cubed per minute. And now we need the equation for surface area, which is 4 pi r squared. You should know that. Also forgot to mention that we do not know dA dt because it's asking the rate of the surface area, how fast is it changing. So we're just going to do dA over dt equals question mark. So we do have our formula written down now. We're just going to differentiate that. We're going to do dA over dt, which is what we don't know, equals 4 pi because these are constants. And then we're going to do 2r, and that's technically to the first power. I just don't usually write it, but just so you could see what I did. R to the first power, you bring the 2 down, reduce the exponent by 1, and then we do dr dt. And that would be our new equation. Again, we plug in, like before, we plug in what we already know. We do not know dA dt, so that will stay the same. 4 pi stays the same, obviously. The 2 stays the same. Our radius we know is 5 feet. 5 to the first power is obviously 5. And we know that dr dt is, because we just solved for that, is 1 foot cubed per minute. So I will plug in 1 for that. Now, we're just going to multiply all these together, and that will get us dA dt, because it's already by itself, so we don't have to do any like multiplication or division or anything like that. It'll just give us the answer right away. So dA over dt equals at 40 pi feet squared per minute. And that would be your final answer. Your surface area is increasing at 40 pi feet squared per minute. Final question. The top of a 15-foot ladder rests against a vertical wall with the bottom of the ladder on level ground as shown in the figure. The ladder is sliding down the wall at a constant rate of 2 feet per second. At what rate, in radians per second, is the acute angle between the bottom of the ladder and the ground changing at the instant the bottom of the ladder is 9 feet from the base of the wall? This is my little drawing right there with the ladder leaning up against the wall. Now this is a really wordy question, which, at least for me, would be really intimidating. It actually took me a while to be able to solve these questions by myself. I thought they were definitely one of the most difficult related rates problems that I've come across so far. So we're going to break this down and do it step by step so you can see how to actually solve these problems with not too much of a struggle. So the first thing it tells us is the top of a 15-foot ladder. So we know that the ladder is 15 feet. This quantity is not changing because the length of the ladder is not changing. It's a constant. Then it says it is sliding down the wall at a constant rate of 2 feet per second. So this is a rate. I've labeled each side of the figure A, B, and C just so we can know what side we're talking about. Just makes things a little bit easier. Now, it says that it's sliding down the wall at 2 feet per second. So basically, when it's sliding down the wall, this is changing, the height of this is changing, B is changing. And because it is a rate, we're going to write dB over dt equals -2 feet per second because it's sliding down. So it's a decrease. Now it wants to know at what rate is the acute angle between the bottom of the ladder and the ground changing at the instant the bottom of the ladder is 9 feet from the base of the wall. So it's asking at what rate is the angle changing. So we're going to call this theta. And they want to know the rate that angle is changing. So we're going to call it d theta dt. I'm going to put a question mark by it because that's what it's asking. We don't know that yet. But I do recognize that this is a 3, 4, 5 triangle. So knowing that, I know that B would be 12 feet. So that just helps us a little bit. So B is 12 feet because it is a 3, 4, 5 triangle. Over here we have dB dt. We've written that we don't know d theta dt. We can just write again over here so we have everything all together. C equals 15 feet and B is 12 feet. A equals 9 feet. Now that we have everything, the next step I'm going to take is I'm going to use the sine equation. So sine theta equals b over 15 because we have opposite over hypotenuse. The hypotenuse, your c value is always constant. That's your constant. However, your b is changing, so you can't put 12 there. You have to put the letter because it's not always 12. The only reason we have 15 there instead of c is because, like I said, it is a constant. So now we have to differentiate this like any of the other equations we've been doing. We should know that the derivative of sine theta is cosine theta, d theta dt, because we're differentiating, equals, and I'm going to write 1/15 dB dt because basically you could have written this out as b times 1/15. So I was just differentiating there. Now that we have this new equation, we can start plugging in values that we have like we've done in the past with our other two problems. So because we have cosine now, cosine theta, we want to put in numbers for that. And the way that we do that is we remember that cosine equals adjacent over hypotenuse. So in relation to the angle, our adjacent side is 9, our hypotenuse is 15. So that's what we're going to plug in for that. So 9 over 15. D theta dt, we don't know. We have a big question mark next to it. That's going to be our final answer. That's what we're looking for. So we still don't know that because we have not reached the end of the problem. And that's going to equal 1/15. So we already have that number. And dB dt is negative 2 feet per second. We figured that out before and wrote that down. And now we're going to first multiply these two values together. So 1/15 times negative 2. Let me just put that in my calculator. 1/15 times negative 2. That's going to give us negative 2/15. So negative 2/15 equals 9/15 d theta dt. Now to isolate d theta dt, we're going to have to divide this quantity out. So we're going to do 9/15 divided by 9/15. That canceled out, and now we're going to have to do negative 2/15 divided by 9/15. So negative 2/15 divided by 9/15. And that gives us a final answer of negative 2/9. So that would be our answer. The question asked what rate in radians per second is the acute angle between the bottom of the ladder and the ground changing. At the instant the bottom of the ladder is 9 feet from the base of the wall. So the rate at which theta is changing at this time is negative 2/9 radians per second. And that is our final problem. I hope this helped you in some way as far as understanding and figuring out how to complete related rates questions. So thank you for watching, and I hope I get a couple points on my average for this extra credit.